All right, hello class. So we're going to go through this practice test real quick. So the first question was they kind of gave it away in both aspects of A and B. They said that the average volume of a white dwarf was kind of the size of Earth. So you just had to take Earth's volume and the mass of the sun, and you do a density calculation, and that'll give you the answer for how dense it is. So they kind of gave away both of those. So I'm going to skip over that real quick. So if we're going to Wally's sandstorm here, and so Wally and Eva became trapped within a harsh sandstorm on the way to Wally's home just before the storm hit. They estimated that his home was 8 kilometers due north of their current location. However, when the storm clears, they discover that it have actually traveled 7 kilometers, excuse me, at 70 degrees north of east, determined how far and which direction they must now travel to get home so that Wally can embarrass himself in front of her by use of a vector diagram drawn to scale. So you guys have your diagram on this PDF here that you can go ahead and, how about this? So if we go ahead and oh, I cannot screen share on this. This isn't Zoom. Okay, so I'm just going to draw this not to scale, but just to give you some sort of idea. So if we have this here, right, and this is about 70 degrees here, again, not drawn to scale, you have better tools than I do, and they have their home right about here at 8 kilometers. So all you have to do for this is very quickly, you can just say that the the adjacent part of this and the opposite part of this using your trig functions that we've been doing all year. We have A here, we have opposite here, and so then we just have opposite adjacent, and we can just write those out. And so the adjacent is just going to be 7 times, let's see, this is adjacent. Yep, this is going to be cosine of 70 degrees. And I've done the calculation here, and this gives you about 6.6 kilometers. Okay, that's a little bit off the edge, but that's a 6.6. And so then this is just the opposite here. And so this is going to be 7 times sine of 70 degrees, and that will yield us 2.3. I guess if we round up, this is 2.4 kilometers. And so now we've basically gotten what we needed. So they need to go back 2.4 kilometers to the west, and then they need to go 8 minus 6.6, so they need to go 1.4 kilometers more north. So they did pretty well. So this is the component method, and so you guys can draw on your own of the vector diagram to scale, and that'll come out relatively quickly. There was no torque equations on this, and the next one is also a pretty simple one. We're talking about how Kanye loves Kanye, who would be my favorite, personally my favorite musician. And so if we see this, it goes, all right, well, from his at rest position, he uniformly accelerates to 4 meters per second. So if we're having a velocity graph here, right, and he goes ahead and he uniformly accelerates to his 4 meters per second up here. And that's this line here. And so in 2 seconds, so in order to get the acceleration, you take, or your average acceleration A, you're gonna, and since it's uniform, your average acceleration equals your initial acceleration equals your final acceleration. So here we just have that Vf minus Vi over delta t here. And so then our initial velocity here is 0, so we just get rid of that. And so then this is just Vf over delta t. So 4 meters per second over 2 seconds. So his A is going to be equal to 2 meters per second squared. And so then you can draw that on your acceleration graph. It's just a constant line for those 2 seconds. He maintains the speed for 3 seconds. So your velocity graph for now, so this is 2 seconds here. We'll say this is 2s, and then for 3 seconds, we'll draw that a little longer. So now this is a total, this is at 5 seconds now for just accounting from 0. And then before realizing that, and so then he slows down to a halt just in front of the mirror within 4 seconds. So then you do the opposite calculation. So where now in this case, your VI, your VF is going to be your 0. So this goes to 0, and now this one is 4 meters per second here. And so then this is negative. So then so we're going to call this one A1, and then A2 is just going to be 0, and then A3 is going to be what happens is, so we have 4 seconds now, so it's going to be 4 over 4, and so then this is going to be 1 meters per second squared. And so your acceleration graph is going to look like a straight line at 2 meters per second, and then it's going to have 0 for this 3 second period, and then it's going to have 1, but this is actually a negative 1, and so then the acceleration graph is going to drop down and be negative. And so then that covers the acceleration graph, and you can go ahead and see exactly where this will get you with your position graph pretty easily here. You'll see that. So if the area under the curves here is going to be your position, and so we're going to say that this is going to be less slopey than it was before. And then he's going to get to 0 here, 0 velocity here at, this will be 9 seconds. And so then the area under the curve here is going to be our position. So so if you can just take the areas of the triangles and the area of the rectangle there, and that will give you your position. And so you can sketch pretty easily the position from this graph here. So say if you were to take a 1 second interval here, because we're trying to do this as accurately as possible, you can take another subdivision here. And so then, since it's uniform acceleration, you're going to have that this is going to be 2 meters per second at 1 second. And so then you can see that this triangle here is going to be 1/2 BH. And so the base is going to be 1 times 2 divided by 2. So that's going to be 1 meter that he travels in the first second. And then here you can see that this is going to be 2 times 2 divided by 2. So that's going to be 2 meters in the second. So then that puts him at 3 meters that he has traveled within the first 2 seconds. And then the position is then going to grow linearly here because this is a flat line, right? And we see that with the acceleration, how the velocity grows in a linear fashion when you have an acceleration. And so then from here we can see, all right, well, if we break this down into 1 second intervals here, you'll have 3 different intervals. So for the first the intervals are going to be the same here because they all have the same area. So you have 1 times 4, so he's going to travel 4 meters in the 3rd second, 4 meters in the 4th second, and 4 meters in the last second. And so you can do the same thing for the last one. You can break it into 4 different second intervals and then take the area of each of those. But in this case, you're going to have your slope here is going to be a -1. And so that changes things just a little bit. It doesn't make it as clean, as nice, but you can still do this math and figure out how far he goes in those 9 seconds. Okay, so I'm going to move on just for the sake of time here. And so Next, we have Long Live the King, and we'll try to zoom through this pretty quickly. So, assuming his fall is strictly in the y direction, there's no air resistance, what is Mufasa's velocity just before impact? So this is just v is equal to gt, and so that'll quickly yield your final velocity, and that just looks like v is equal to at. And usually you'll have an initial velocity here, but he starts from rest when he falls. And so next up, we're going to have b. What is the terminal velocity is 40 meters per second. Does he reach terminal velocity? And if so, how long does it take? So the time is, first of all, it's yes. So then you take that velocity and divide it by the value for gravity, and that'll give you your time. So you basically just rearranging this and then putting a t here, and then saying that t is equal to vt over a, which is in this case g. So we can erase that and put g there. And so vt is our 40 value that we're given in the problem, and then you resolve it, and it does give you the time, which ends up being a little bit over 4 seconds, closer to 4.1. So next up, we're going to say how tall is the cliff, and so then you just need your basic kinematic equation where y is equal to 1/2 at squared plus v naught y t plus y naught. And so it just depends on how you take your initial conditions. The simplest way to attack this problem is just to set y naught equal to 0, and since v naught is equal to 0, since he starts from rest, or starts his fall from rest, you just set that equal to 0, and you just get that y is going to be equal to 1/2 gt squared. And you have the time that it takes. It's given in the problem, and so this is an easy one to do. So then now we're kind of reversing the problem, saying assume now that you only caught a glimpse at the very end of the fall, and only information that you have is the height of the cliff and the velocity just before impact. Determine the time of this fall, and make sure to show all your work. So this is just a little bit of a backwards problem. So you just take the height or the velocity that you have and divide it by your value for g, and that will give you your time here. And so you're just basically doing this again, but with your velocity plugged back in. So you're just taking away the terminal part and using the velocity that you've already calculated. And so this is a very quick one. And E, drop it in the comments. How long did it take you to cry on this problem? Okay, so next up we're going to have the Batglum. And so this is a little bit of a weird problem, just because even though it says that he's swinging from a long distance, which would mean theta is large, it says to treat the problem like a simple pendulum. And so in this case, we just use our equation for t for a simple pendulum, and this is going to be 2 pi times the square root of L over g. And so that'll just give you 6.949 seconds for t, and then you just take that per period. So you have one period takes 6.9 seconds, and that gives you 1.439 periods per second. And we know that mass has no effect here because the mass cancels out in this case. Moving quickly, this is actually one of the slightly complicated problems just because it has a bunch of parts. So you have to do a couple things here. So this is probably one of the most complete problems because it involves energy, and it involves a whole bunch of different types of physics that we covered in the first half of the semester. So a couple things. You don't have to talk about the density and the volume of the arrow until later. And so we can save that until D, but that's pretty easy. But then that factors into the kinetic energy side of the problem. So the initial firing speed of the arrow. So we get that originally that the arrow is in flight for 4.1 seconds and travels a distance of 150 meters. So one thing that we know about velocity in the x direction is that it's unchanging and its acceleration is equal to 0. So we can just take the distance and divide it by 4.1, and that average velocity gives us the initial velocity and the final velocity. So very quickly, all you need to do is do exactly that. 50 divided by 4.1, and that will yield us 36.59 meters per second. This is meters, this is seconds. And so there's your answer for A. What are the x and y components of the arrow's velocity? And so we've done this plenty of times before. So in this case, we're just correcting for drop, and that's going to be the only part of the y velocity. So because the arrow is shot horizontally at theta is equal to 0. So in this case, we just have to account for drop, and then a drop in this case is just going to be, if I can find it, yeah, it's just going to be the time that the arrow is at flight times gravity, and that'll give you 40 meters per second. It's 40.22. Okay, so then to find the total component, you just use Pythagorean theorem, and then so your total V here is going to be 54.37 meters per second. So this thing's really moving here. It's really, really moving. Okay, so now next thing it says, how far does the arrow fall? And then again, you just have to use our equation for last time, where y is going to be equal to 1/2 gt squared, because there's no velocity in the y direction. And so this easily yields 82.45 meters. So this thing drops quite a bit actually here. Okay, so moving on, we have calculate the mass of the arrow, assuming it is cylindrical, and then use it to find the kinetic energy. So we have our V here, and this is going to be used in our kinetic energy calculation. Also, if you're finding the angle here, all you have to do is use the inverse tangent function, and that'll spit it out really quick. So the volume for a cylinder is just going to be 2 pi RL, and so then we just multiply it by the density to get the mass. So this equation here will give you your mass. And so we're given the we have L is 2 meters, and we have our diameter is 1 centimeter, so this is now 1/2 centimeter for R. Multiply that. I guess you can really, if you really want to, get rid of the 2R and just say that this is D, and that simplifies it a little bit. So you just have DL pi rho, and that'll yield you your mass, and the mass of the arrow is going to end up being 1.37 kilometers, or not kilometers, kilograms. Okay, so you take your kinetic energy equation here for this. This is Ke is equal to 1/2 mv squared. You plug in your values here. This here, oh no, this here, and this will spit out 4,050 joules. So this thing's really moving here, or 4.05 kilojoules, whatever you want, really. So then in this case, now we have to find, the last part is we have to find the spring constant of the bow. So we know that U has to equal Ke, and so then U here is going to be 1/2 kx squared, and so then you set that equal to this, and it gives you that it was displaced by 1 meter, which makes this really simple, because then this is just 1 and it just doesn't matter. And so then you just at this point you just set this equal to this, and I think I halved it by accident. Oh, yikes. Okay, so you just multiply the 2 to the other side, and that gives you K is equal to like 8,100 joules of energy. And So then that's your spring constant. Except this is not in joules. This is joules per meter squared, and that'll give you K. Okay. Okay, very nice. All right, we got that down. And so in the film, the arrow strikes Smaug at the height at or near the bard on the tower and pierces his hide nearly horizontally. Is this realistic by any means? No, it is not. There's no need to email Peter Jackson here. Please leave him out of it. Um, People have probably solved this test before in email, and he's probably tired of it. Okay, well, let's move on. All right, so 7, we have the pancakeification of a Goomba. That ends that page. So this is a little wacky problem. So first thing we have to do is we have to calculate gravity. So then in this case, we just have to take our height equation. So h is equal to 1/2 gt squared, and we have to rearrange that for g. But so to find our new g, so you take 2 to the other side. So then you have 7.5 times 2 is 15, 15, and then divided by the time squared, and that ends up giving you about 188.6 meters per second squared, which is fairly large. Yeah, because that's a very small time interval. Okay, so we found gravity that way. Determine the velocity just as he hits the Goomba's head. So we take our gravity multiplied by the time. That'll give you 53.18 meters per second. And then, so that's pretty simple. Assuming Mario to be of average weight for his age and height is determined that he weighs 57 kilograms. The collision between Mario and the Goomba, which lasts about 0.5 seconds, is elastic as it bounces off his head at, say, 6 meters per second. Find the initial and final momenta of Mario before and after the impulse and the force of the impact. So very quickly we can find what the initial momenta is, and so that's just 53.8 or 1/8 times his mass, because we're just using our simple momentum equation. So that gives you around negative 3,031.56 kilograms meters per second. And that's negative because his velocity is in the downward direction. So you have to account for that. And then P, or its final momenta, is going to be its mass again times the velocity they give you in the problem, and that'll give you 342 kilograms per meters times meters per second. And so then the impulse is just the difference between those two. So the first one's positive, the second one's negative, and that negative cancels out with the negative in the 3,000 number, and so then that'll give you that the impulse is about 3,374.75 if you round up kilograms meters per second. So then in order to find the force, we've been through all this in our problems. We just take the momenta divided by the time of collision, and so then that'll give you about 67,000 newtons, which is quite a lot. So then at the end of the problem, it says the strongest bone in the human body, the femur, can break if 4,000 newtons of force is applied to it. 67,000 is obviously more than 40,000. So yes, this Goomba is rightfully pancaked. It is rightfully squished to a pulp, considering that this is more than or close to 17 times the amount of force to break one femur. It would crush you. So next up, we'll go to artificial gravity, and the end of this problem is a little tricky, and I kind of liked it actually. So the movie Interstellar features a spinning spacecraft named Endurance with a radius of 31 meters. Since there's no gravitational forces in space, the Endurance spins to create a centripetal force, which gives an inward pointing acceleration that mimics gravity, gives the sensation of weight. In order to simulate the acceleration due to gravity on Earth, what would the angular frequency of the Endurance have to be? So we know that g is going to be equal to 9.81, yes, meters per second. So we can set that equal to our centrifugal acceleration equation, which is vt squared over r. So you set that equal to each other. You solve for vt. So you multiply it both sides by r, take the square root. That'll give you your vt. Plug your numbers in. And then you should get that is about 17.5 whatever meters per second. Now we have to find the angular frequency. So we just take our angular frequency equation, which is just going to be omega is equal to Vt over r. So then you divide that number by 31, and that gives you a little over half a radian per second. And then the problem wants it in RPM, so you just do that conversion very quickly. And so that'll give you the answer to the first question, which is what is the angular frequency? So we've covered that. Next up, objects at different radii experience different accelerations, and since an astronaut being about 2 meters tall would experience different accelerations at his head compared to his feet, so then we want to find what's going to be the I believe it's we're finding the acceleration of his head. So now we have to take our angular frequency that we just found and go backwards. But this time, instead, we're going to be multiplying by 29 instead of 30, or instead of dividing by 30. So we're doing the reverse process here. And so then that's going to give you a tangential velocity of 16.314 meters per second. And then you just have to replug your Vt back into your equation for your centripetal acceleration, square it, and divide by your new r of 29, and that'll give you 9.17 meters per second squared. And furthermore, different parts of the astronaut's body, and you can just do percent difference. It's just based on a formula you can look up. Furthermore, different parts of the astronaut's body are moving at different velocities, since the feet are moving in a larger circle than the head, but at the same angular frequency. Determine the velocity of the astronaut's feet and that of his head. We've already done that based on these calculations here. It is often noted that the angular velocity should be limited to 2 RPMs, so about 0.2 radians per second, so that these effects are minimized. To maintain the same amount of artificial gravity before the ship would need to be larger, what would its radius have to be in this case? So this one's a little tricky, and this is why I like it. So you have to set the gravity equation the gravity number 9.81 to your centripetal acceleration Vt squared over r. And then you have to divide that equation by the equation that's given here. So that's 0.21 radians per second is equal to Vt over r. And doing this will yield you what your tangential velocity should be in order to go ahead and simulate this artificial gravity at this angular frequency that they want you to. And so that'll give you about 46.7 meters per second. And so then you plug that back into your original angular frequency equation, which is going to be r omega is equal to Vt, and then you solve for r. And so then you take Vt, divide by your your new value for omega, and that'll give you your radius should be about 222 meters for how big this ship should be. Okay, and so 9 was kind of a lab question where we can cut that one out. Don't have to do that. And so then I kind of ballparked the Justin Bieber problem because it is a bonus problem, and I really didn't actually feel like doing it. So my approach was to guesstimate how far Bieber runs when the Velociraptor gets to the other cage. So the Velociraptor is going to cover that distance, that 400 meters, in 11.11 seconds. And so then, but in that time period, that it takes the Velociraptor to get to the cage itself, Justin Bieber's only traveled 26.66 meters. And so this Velociraptor can cover that distance in less than a second. And we can go ahead and calculate what that actually is. You just take 26 and divide it by 36. That's going to give you 13 over 18 basically. And actually, if you round it up to 27, that gives you 3/4. So it'd be 3/4 of a second. So basically, Bieber's going to be caught in about 12 seconds.
and that should be relatively actually very close to the actual answer. It should only be off by a fraction of a second. So I just called it quits and said that he goes ahead and catches it in 12 seconds. Okay, good luck on your exam. I hope everybody does well. Uh, I hope everybody's studied hard, and I hope you guys, again, do well. Have a good day.